Okay guys, welcome everyone to another mini lecture. So today we're talking about binary search trees, what they are and why we need them. A quick 5-minute introduction, okay? So what's a binary search tree? It certainly sounds cool, but do we really need them? So essentially, the basic contention that we have is between arrays and linked lists or a list. The structure of an array is essentially represents a contiguous block of memory. And when we say contiguous block of memory, we mean, at least from the application layer's perspective, typically from a programmer's perspective, we think we have a long block of memory. The operating system may or may not actually have that contiguous block of memory assigned, but from our programmer's perspective, we feel we have this memory and we can kind of do the memory arithmetic on that. That's basically what we have, and then the arrays allow us random access. So random access essentially means that if we have a 10,000 element array, we can quickly access any specific location just as quickly as we can access the first location or the last location, etc. So random access means that we can access any location in constant amount of time. However, we cannot insert a new element in the middle of the array. We can put a new element there, but then we have to shift everything, and that can take time. So if we want to put a new element there in the middle, then we'd have to shift half of the array down, which can then take time. A linked list is different in that we don't have a contiguous block of memory, but we have different blocks of memory all around the memory universe, which are connected via pointers. Pointers, whether they look like C pointers or not, doesn't matter, but they're essentially connected via memory addresses. So that means we cannot access we don't have random access. We cannot say, oh, give me the 812th element or 9,630th element, but we can follow the pointers to say, okay, give me the next, give me the next, give me the next. So it can take us some time to get a specific element, so there's no random access. However, when we are at a location, we can do something to say, okay, we're now going to have a new element here, and that element is going to become between these two elements that we had earlier, like X and Y. Now we want to put a Z in between. Perfectly fine, no problem. So that translates to sorting and searching operations running differently. Then in array, you can search the array by first sorting it in n log n time, and then searching it in some kind of a binary search way in only log n time. In a linked list, you can add or delete elements in order 1 time, that means constant time, but it does take you n log n time to sort, and even searching takes order n time because traversal itself takes order n time. So that's our basic contention here. In contrast to these, the time complexity of a binary search tree is order log n for any insert, delete, or search operation. And now how does that manifest? What that does is that in terms of a mixed operation kind of environment, binary search trees are almost mandatory to use. That means that, let's take this scenario that we have 1 million inserts, couple of million searches, 1 million deletes. So in this case, the linked list will be able to do the inserts very quickly. However, the 2 million searches will take a long time, and the deletes will again take short amount of time. The array will take the inserts will take a very long time, the searches will be shorter, and the deletes will again take a long time. So both of them will actually take about 2 trillion operations. In a binary search tree, each of these operations will take 1 million, will take about 20 units. 20 is the log of 1 million. So we'll take about 20. So log of 1 million to the base 2 is about 20. So the binary search tree will take about 20 operations in each of these cases. So 1 million times 20, 2 million times 20, 1 million times 20, so that's a total of only 80 million. So that makes it 20,000 times faster than either a linked list or an array. which is a big difference. So if you see a sophisticated kind of program, anything that's not trivial, you'll find that it's always using the memory, the structure in a correct way, many times using a binary search tree, not using an array or a linked list. So now we agree that binary search trees sound cool, they are cool. Now the question is, how can we actually build them? Now this presentation will not go into great detail, but just to give you a little preview of it, what is a binary search tree, or what is even a binary tree? Binary tree is just a tree that has up to 2 child nodes. So that means you won't have a third child node here. But other than that, this is a perfectly good binary tree. This node does not have 2 child nodes. This one has only 1. Either way, it's fine as long as no node has more than 2 child nodes. Now, it is more efficient and interesting if the binary tree is height balanced. We'll talk about that again in a moment. If you just have a very tall and unbalanced binary tree, that is a binary tree, but it will kind of behave like a linked list. So the whole question is that you're going to be trying to keep it height balanced. Now, what is the difference between a binary search tree and a binary tree? Not very much, actually. Binary search tree is just a binary tree where each node contains a value. So you are essentially using the binary tree to store the values, and you sort those values in a certain sorted property. That a good example of a sorting property can be that for when you have a node, the left subtree contains the values that are less than equal to, right subtree contains the values that are greater than equal to. So it has that, essentially, that sorting property. So it's a binary tree that has the values in each node, and those are sorted by value. Binary search trees support 3 different operations: insert, delete, and search, kind of like we discussed. And like we said, they are more interesting if binary search trees are height balanced. There are many implementations of this binary search tree concept. The 2 good examples are red-black tree and AVL trees. There are many others as well. Now the word that we are using is insert. It's kind of the same as add, but we call it insert so that it inserts the value but then also maintains some structural property of that binary search tree. So like we said, the binary search tree, if it's too lopsided, that's not going to work very well. So as long as the height is limited by log n, the time complexity of each operation will also be limited by log n, because the binary search trees typically you start from the root and go down to the leaf nodes here. So as long as your height is limited by log n, your time will also be limited by log n. There are many kinds of height balance. You could say there's a red-black tree which has a specific implementation. You can have a very strict definition. You can have a very loose definition, like saying, okay, it's okay if one side is up to 2 times taller than the other one, or up to 10 times taller than the other one. And as crazy as it sounds, even if you say that either side can be up to 100 times taller than the other one, it sounds that, oh, that can be pretty lopsided. But as long as you maintain some constant bound on that, all of these will meet the order log n performance guarantee of the binary search trees. And the basic idea of height balance and how do you maintain it is to do some kind of rotation, some kind of adjustment, that when you insert something, for example, in this case, let's suppose we have 10, 15 binary search tree, you add 20, now the tree looks like this, but it looks like lopsided. You can rotate it, you can adjust it so it becomes 15, 10, 20. So this is also a binary search tree. This is also a binary search tree, but this has a better height balance compared to this. All of them have 3 values in it. They are both have the sorting property. For example, 10, 15 is to the right, 20 is to the right, but this one has a better height balance. And binary search trees are very easy to find. You can easily find them in the Java itself from the tree map. It's a basic implementation of a tree map, is one implementation of map interface. It's an implementation of red-black trees. And you can always find the source code of any Java class just by searching, by looking it up. And you can look at the tree map source, and you can find on how does it actually handle the red-black tree. So you can read more about it. This video doesn't go too much into it, but we do want to summarize here to say that the binary search trees, they are great data structure. They're almost critical if you're doing any kind of mixed use, which is mostly the time. That means you're adding values, you're searching values, you're deleting values. In that case, using either the array or the linked list will often not be the right outcome for you because it'll take too long in one of those kinds of operations. So in that case, it's almost mandatory that you should consider using a kind of a binary search tree. You can deepen this understanding by studying a specific implementation of binary search trees such as red-black trees, but hopefully by now you have a good enough understanding of what binary search trees are and how to use them.